Thank you, everyone, for joining. This is now webinar number 15. We're going to be touching, going over 1,4-dioxane. I keep saying we're going to do everything you need to know about 1,4-dioxane. Let's just keep it to the 5 basic things we want to do. Something that I personally found very interesting about 1,4-dioxane, or we'll just leave it to dioxane to keep it short, was while there aren't any federal regulations, at least not in the US or Canada, it's primarily more federal mandated or province-wide. So it's something that you won't actually find in a standard water report, yet you'll see it in your shampoo, from nail polish to soaps to cleaning products. So it is something that's coming up. And you're obviously not drinking your shampoo, I hope not, but it is something that will eventually get to our water anyways. So it's something that's actually showing up a little bit more, and there has been some push towards regulations. So today, our guest today is going to be Dr. Orren Scheider. Let's give him another minute to connect. He's from Aclarity out of Boston, Massachusetts. He is physically in New Jersey, and he's going to be joining us shortly. So this is now number 15 of some of the webinars that we're doing. We've been going through them. I know that the last bit have been kind of changing around a little bit just for the order due to some everybody's calendars. In October, we're focusing on emerging contaminants month. These are some of the ones that we're going to be covering. Cyanotoxins and cyanobacteria is one that I'm personally looking forward to that we're going to be doing next week. So far, we've already done PFAS and microplastics. A fun bit about microplastics, we threw it out there to see, who's one of the bigger contributors to microplastics, and it wasn't just microplastics. It also had to do with microfibers. So we kind of threw it out there in social media to see any of the comments that we'd got there. We got 1.3 million views and close to 13,000 comments and likes, all focusing on microplastics and who should be responsible. Is it the consumer? Is it the manufacturer? Is it regulators? So yeah, so that's kind of interesting when you actually get it out there and get people's response. So for those of you that this is your first time logging in, AWC, who we are. So AWC Solutions, we design and manufacture water treatment plants. We have been around now for over 40 years. We have close to 600 water treatment plants worldwide. That's not just in North America, but as we grow and expand into other countries, that includes going into Latin America. We have a few upcoming projects that we're bidding on in Chile and in Costa Rica, and in Mexico, so exciting stuff. So we break down our units, into 3 different categories. You've got your standard potable water, so something like a DAF or ST plant. Then we've got everything that has to do with wastewater, and of course we do some of these skid-mounted systems. When you go into desalination, you're focusing more on a skid-mounted system paired up with some kind of pre-filtration. So with that, we will bring it over to 1,4-dioxane. We're going to give Dr. Scheider another minute to connect. I believe I was just on the phone with him, and he might be on here already.
I am here, Alex.
There we go. Welcome, Dr. Scheider.
Thank you very much.
So I gave a short introduction to Aclarity, but with that, you see my screen. You can go ahead and take it away on your end.
Okay, very good. Let me just pop up my screen here, pick up where you left off. Here we go. Okay, so dioxane, it's, more concern is arising of it. I hate to use the term emerging contaminants. They're not emerging from anywhere. They're there. They have been for a while. It's our concern that is growing around it and around them. Moving on here, let me get into slideshow mode. There we are. So just briefly, covering these 5 points. What is dioxane? Where it comes from? Why are we concerned about it? The regulations out there, and Alex touched on the lack of federal regulations both in Canada and the US. And then finally, just really quickly, some of the available treatment technologies. As you understand, they'll be doing another webinar in the future, diving more into treatment. So what's dioxane? It's that big molecule in the middle there. It's really a very simple molecule. 4 carbons, 8 hydrogens, 2 oxygens. It's a double ketone in a ring here. It's also known as dioxane, 1,4-D. You'll see all these other things. Commonly, it's you'll see as 1,4-D dioxane or 1,4-dioxane. What makes it both very useful as an industrial chemical, but also problematic from the water perspective, is that it's completely miscible in water. It means you can put in a lot in there. It doesn't start forming a separate phase like you would see with petroleum products. And because it's totally miscible, it's also non-volatile. So, typical for a lot of industrial chemicals, we can use air strippers, other type of air transfer to get it from the water phase into the air phase. That just doesn't happen with dioxane. And that way, it's somewhat similar to MTBE, methylbutyl ether, another ether that is very difficult to get out of water using kind of conventional treatment. It's not biodegradable, so it gets in the groundwater and stays there. It doesn't sorb to soils, so oftentimes it shows up in groundwater plumes prior to chlorinated solvents, which you'll find them together a lot. It was used as the stabilizer for a lot of chlorinated organics, such as trichloroethane, TCA. And TCA was phased out in the 1995 Montreal protocols. So we're not seeing it as much, but it's still, dioxane is still out there and being used in some applications. As I mentioned, it's widely used as a stabilizer for the solvents. It's not a solvent itself, but it helps keep them in a usable form. And it's found in tons of products. Paint strippers, dyes, antifreezes, greases, de-icing fluids, and consumer products like, Alex said, shampoos. So get a nice gloss from your hair from dioxane. We don't see it very much in surface waters. It's almost primarily found in contaminated groundwaters, and along with the chlorinated solvents, as I had mentioned. Health concerns, hey, if you get around a little bit, nausea, drowsiness, irritation of the eyes and nose, but the acute effects aren't too bad. It's the long-term effects that really we have to worry about. It really absorbs very quickly into both the lungs and GI tract, and gets throughout your body. And the US EPA has classified it as a likely carcinogen. Not quite the highest level, but up there. And the EPA's been looking at it for a while. They haven't found it in enough places, federal regulation, but they're leaving that up to the states. And speaking of which, here are the guidelines. There aren't any really hard MCLs, but there are health guidelines in all these states here, and see quite a wide difference, ranging from very low levels in Colorado at 0.35 ppb, micrograms per liter, up to Alaska at 77. So that's 20 times difference there. In Canada, occupational exposure limits, OELs, for the different provinces are also listed there. Not quite the same type of approach that the U.S. uses, where it's concentrations in the water. And now treatment alternatives. What's out there? Typically for many organic species, our tried and true approach is using activated carbon. For solvents, PFAS and other things. For dioxane, because the molecule is so small and it's so miscible in water, it breaks through carbon very rapidly. There isn't much of a holdup there, so it's really not cost effective. You could put it in there and you'd burn through it, depending on loading rates in a month or so. So it just really isn't cost effective. There's no volatility to it, so we can't strip it out using air. There have been some biological treatment processes, some in situ. Some researchers have identified some specific bacterial strains that can break it down, but it's really not widely used. There is some in situ treatment sites that are looking at it, but it's not really widely accepted. There is a out there that uses a specialty sorbent bead that is regenerable. It actually use steam to regenerate it, but it's really, really expensive, especially for small systems. If you had, because it regenerates with steam, you're using a lot of energy to create that steam, and you need the boilers on site on top of the resin, which is much more expensive than standard ion exchange resins. So if you had a really big site with a lot of dioxane, it might be cost effective. But for a generic well that might be 100 GPM, 150 GPM, it's just way too expensive, and I'll show you that in a little bit. And really, right now, the tried and true approach for dioxane is advanced oxidation. On the right-hand side of the picture, there is a Trojan UV Fox system, which is a UV hydrogen peroxide, and that's sort of the go-to approach. There are other ones in New York State. Stony Brook University, working with New York State Department of Health, just completed a big study of 4 different sites using, I think, 6 different technologies to evaluate dioxane treatment. I was on the science advisory board for that. Very interesting. So we looked at ozone peroxide, UV peroxide, a UV titanium dioxide system, and UV chlorine, I think. So, traditional oxidation does not break down the dioxane, but once you get into advanced oxidation with hydroxyl radicals, that will break up the bonds, especially the ether linkages, and break it down into fragments. And more recently, and this is where Aclarity comes in, looking at electrochemistry. Electrochemistry is a subset of advanced oxidation. Doesn't use any chemicals. What it does do is uses enough electricity to break the hydrogen-oxygen bond in water, and that creates ozone, peroxide, and hydroxyl radicals. So it's an in situ way of degrading dioxane. We have lab data showing it can work. We're looking to find some sites where we can actually do some piloting. The nice part is, if you've ever worked with UV systems, when you turn them on, it takes up to 15 minutes for them to warm up. So you're not treating the water in that time. Electrochemical oxidation, it's immediate. You turn it on and start working. So for small wells with intermittent operation, it might be a lot more cost effective. I recently did a project looking at some dioxane treatment at a real well in New Jersey, relatively small, 150 gallons a minute. Not all that high dioxane, 0.5 micrograms per liter, and the target concentration was 0.2. And looked at traditional UV peroxide treatment, the regenerable sorption, and then the electrochemistry. And here are the capex and opex costs for that. You see the sorption just is way too expensive. The electrochemical systems that we were looking at, we're still relatively early stage, and we expect that we'll be able to get our costs down by 30 to 50%, which would certainly bring us in line with the traditional advanced oxidation there. So, from an operability perspective, you can run the electrochemistry remotely. advanced oxidation, you're storing peroxide, which no one really likes to do. It's a pain in the butt. Or using ozone, and then you have change of UV lamps. So there are some other considerations there. So that's really, in a nutshell, dioxane. It's different from a lot of our other, I don't want to say normal, but other routine organic chemicals that we find in groundwaters. It's non-chlorinated. We can't strip it out easily, and there really aren't a ton of treatment options out there. So with that, I'll hand it back to Alex, and here's my contact information. Feel free to contact me with any questions you might have, and I'd be happy to take any questions that are out there. Thank you.
Thank you, Orren. Want to make sure my mic's back on. Yes. Okay. There we go. Thank you, Orren. That, like you said, that's in a nutshell. The idea is to try to get as much information as we can off of one of the things. So there's a chat box is open. So if anybody has any questions, go ahead. You can punch them in there. As always, I always have a short little list of questions, which I'll hit you with here in a minute if anybody wants to start typing anything, or don't be shy. You can go ahead and turn your camera on and go over them. So we had kind of covered, where they come from and how they get into our, just in general, aquifers and some of the negative effects on it. How do we do with ecosystems? So, with microplastics, it's pretty straightforward. You're going into not just going into aquifers, but potentially going into something like, your lakes and rivers and streams. Would we see something like 1,4-D getting into a lake where it's affecting some of our wildlife, even if something like fish? Is that something that's ever been studied?
I'm sure it has been. I'm just not aware of it. As I said, it's not really biodegradable, so it could easily travel through the. It's not degradable. It's not absorbed, so it's going to get transported with the water flow. So it could easily end up in streams or lakes. I hadn't really considered that, but I'm sure that's occurring.
Okay, because it turns into a cycle, whether or not it's bioaccumulative in your system, and whether it's going into a lake where you're going affecting wildlife, and then you're potentially eating some of that if you're fishing, right? And how that kind of works into the system. So we won't be touching so much of the treatment, but I did have a question on the activated carbon. You mentioned that it potentially breaks down. Are you worried about it fouling up carbon, breaking down carbon, and lastly, does it compete with any negatively charged ions in water with carbon adsorption?
It doesn't break down the carbon; it breaks through the carbon, so it doesn't stick, very long in the carbon column. Comes through quickly. What I meant by breakthrough, I wouldn't expect it to physically degrade the carbon, at least not on the time scale where the carbon would be absorbing the material and the 1,4-D. So, in turn, it's a non-polar molecule, so there's not really a charge that we're going to be dealing with here that would displace it, because it's not readily sorbed. It's not going to displace anything that is already there. Let's say PFAS or natural organic matter even. So I don't see it interfering much as just it doesn't even pay much attention to the GAC. It just kind of goes right past it.
Right through it. Okay. So now we do have a couple questions here in the chat box. So let's go have a look at them. The first one here is from Andrew Stavano. So the question is, to operate the electrochemical method, what are some of the details of acceptable feed water quality? So, if you're taking a look at your TSS, organics, TDS, alkalinity, et cetera.
Sure. For the TSS, well, we have two different types of electrodes. One is a porous electrode. We need to filter that down to 5 microns, or else it will clog. We also have a solid electrode that you don't have to worry about clogging that, but the surface area is much less. So it's a balance. For the solid electrode, there's a 3 millimeter gap between the anode and the cathode. So, anything that can get through that can get treated. For the porous electrode, it's 5 microns. As far as TDS goes, it's actually the higher the better. The TDS is conductivity, so it carries the current between the cathode and the anode more readily. In RO, permeate water has incredibly high resistivity. You just can't get much current there. Ground, even moderately, a TDS of 125 or 250 would work great in there. Organics, it's really agnostic to organics. It breaks down everything. Typically in groundwaters, we don't see all that much natural organic matter, except if you're in Florida, some in northeastern U.S. and other kind of swampy places. You could get NOM, but that will also be broken down.
So just to follow up on the organic side, because when you say, the Northwest, we're literally right in the Northwest of the U.S., or just above it anyways. Would organics potentially slow down the process where you have to lower your flow rate to maximize your contact time, or would it not negatively affect it in any way?
What it could do is provide additional oxidant demand. The electrochemical oxidation is creating oxidants. The more demand you have, the more you need to treat. Some of that might be governed by the relative rates of reaction between, if dioxane, I don't have the kinetic constants in front of me, dioxane may break down much more quickly than natural organic matter. So there might not be as much of an impact, but all this is things that you would want to do bench testing on. And with the bench test, we take the parameters from that and can translate that into a full-scale flow-through system. Okay.
So we have another 2 questions, and funny enough, we said we were going to do a separate webinar to cover the actual treatment for dioxane, which we will, but we'll go ahead and put these in here. So question number 1 is, what's the max removal ability of an electrochemical method? And the second one, would RO concentrate the dioxane? So I'm guessing it's similar to, you use RO to concentrate your dioxane, and then you can use some other form of treatment to treat the dioxane stream, or the waste stream.
I'll go to the second one first about RO. As a non-polar molecule, I'd expect dioxane actually to pass right through RO. It's small, non-polar, so I'd see it, similar to water in that sense. You can push it through the pores. You're not doing a charge separation like you are with ions. So I don't think it would concentrate it, which is also why you don't see RO as a treatment method for dioxane. In terms of the max removal capacity, and be touching on this in a couple of weeks, electrochemistry can mineralize, can degrade PFAS. So, and we've done testing with PFAS up to 300 milligrams per liter. So there isn't a real maximum level. It's just going to require more modules to use. And that picture that I showed before of the Aclarity system, that's a single module. We're working on creating systems where we pack multiple modules within a single pressure vessel, and then could put multiple pressure vessels together into skids and trains, much like RO. So, if you had just a lot of it and high flows, you would need modules, but that becomes the function of economics rather than a technical hurdle to challenge, to conquer. Excuse me.
Right. Well, let's make sure we leave a little extra for next month when we actually dig or a little, go into the how we're treating it and other alternatives. So with that, we're going to wrap up. Thank you very much for coming, Dr. Scheider. For those you, there's a contact information on there. You can shoot him a quick email. My information is in there as well. I do want to add just saying we are going to be doing cyanotoxins next week again, same time. Shameful plug. We are everything is going up on the YouTube channel. This will be up there in the next 24 hours if you want to share it, but you'll be getting an email with the recording link, so it's on there. If anybody wants to stick around and have any more questions, we can do that. We'll go ahead and stop the recording right now. And thank you very much for your time, and I will see you next week. Bye.